So we did our imports, we made the data set, and then we made the data loader. So that takes in the data set which we want to load from. And then we'll say shuffle equals true. So each epoch, when we load from that data set, we'll shuffle the data set. And it also takes in batch size as the batch size which we defined before. Okay. Run that, check it's all good. All right. If you guys are running that, it will probably give you a download bar. And then it will install it into that fashion data folder. Okay. Now what we're going to do is we're going to make the discriminator. So in every session done before, we've basically just trained one model. Now we're going to train two. So we're going to have two separate classes, one for the discriminator, one for the generator. So we'll say class discriminator inherits from what? Sorry? torch.nn.module. Yeah, torch.nn.module. Cool. And then that will have a constructor, so we'll initialize that. What are we going to give it? Nothing except self. And then we'll say, so we'll initialize the parent class, super initialize the parent class. And then we'll say, we'll define some convolutional layers. So we'll say self.conv1 is equal to torch.nn.conv2d 1 by 64 by so yeah, it takes in one channel because this is grayscale. So yeah, sorry to walk through. Yeah, convolutional layer, one channel. We're going to find 64 different activation maps from that. We'll say a kernel size of 4, and then we'll say a stride of 1. So actually, so I'm just going to stick to my script because otherwise it will break all the dimensions and we'll have to debug it. 1 to 64, kernel size of 4, stride of 2.
Why do you use a new kernel size?
Sorry?
Why do you need
It doesn't really matter. It's just this works out for the dimensions. I might have played around with it, I think. Yeah. Okay. Cool. And then we'll say padding equals 1. So that's padding. That's yeah, stride there. That's kernel size. That's in channels and out channels. Okay, cool. All right. Then we'll say self.conv2 is equal to torch.nn. Again, another convolutional layer, conv2d. Now from 64 to, we'll say 128, with a kernel size equal to 4. Again, stride equals 2, and then padding equals 1. And you can play around with all these things, obviously, and just explore what works. Cool, so 2 convolutional layers, and then we'll say our discriminator is going to take these, it's going to convolve over our image twice, and then we're going to have a fully connected layer after that. So we'll say self.fully connected is equal to torch.nn.linear. Torch.nn.linear. That's going to take in. So with these dimensions, I know because I've done it already, the activation map size after these 2 convolutions is going to be 7 by 7, and we've got 128 channels. So what we're gonna, the input we're gonna give to this is this unrolled output of this convolutional layer, which is going to be 128 by 7 by 7 dimensional vector. Okay, and then we're going to take that. to a single number, which will be our confidence that this is a real example. Okay. Then what we'll also do is we'll define our batch normalization layers. So torch.nn.batch norm, with a capital B, capital M, and then 2D. And what this takes in is the number of either channels or units in that layer. So in this case, we're going to have we're going to have batch size, which is going to be 128, as I put it up there. Better to put that as batch size. It's kind of a rough implementation, but obviously I think it would be better to put variables here. And you could just change one variable, like channels, and then it will change both of those or something. Okay, cool. So we've got our first batch normalization layer. We'll make another. We'll call that torch.nn. We'll call it self.bn2 batch norm. This is for the second convolutional layer, which then takes in. That one's going to take in 64. So that's the batch normalization we're going to apply to the output of this layer. This is the batch normalization we're going to apply to the output of this layer. Okay. So we defined our layers. Then we'll define what happens when we put an input into our model. So what happens when we do the forward pass. The forward pass for this instance of the class takes in an input, x, and we'll say that x is firstly self.conv1 of x. Then we're going to apply batch norm, so self.bn1 on x, and then we'll apply an activation function. So should we do that? We'll actually define an activation function here. We'll say torch.nn.sigmoid. Create that submodule there. And then we'll be able to say self.activation function on x. Okay. We'll say x equals self.conv2 on the output of that. And then we'll apply batch normalization in the second layer. So these batch norms as well, they're not just operations, like they're actual layers, because they have parameters. They have those scaling and shifting parameters. Okay. So keep going. Now we're going to apply another. We're going to apply another activation function to the output of that batch norm. And then what we're going to do is we're going to reshape x, x.view. So it's come out of our convolutional layer, right? Batch norm and the activation functions don't change the size. And so now we want the input to be this size. So if we're going to view it as -128 by 7 by 7, and the -1 is there because so I'm saying I want it to have this many columns, and I don't care how many rows, because the rows represent the number of items in the batch. And if we don't have an exact integer multiple of batch size as the size of our training data set, then we can't put this as like a 16, because it might come out as a 15 or something like that, right? So we'll put it as -1, then it doesn't matter. Okay. And so now we can pass it into our fully convolutional layers. So we'll say pass x through there, x is equal to self dot fully convolutional. Sorry, fully connected. That's not fully convolutional. Like that. And then we'll apply our we'll apply on the end of that. Okay, sorry, yeah, we won't have sigmoids or activation. What we have relu, and then we'll do self dot sigmoid is equal to torch dot nn dot sigmoid. So we'll put our output through a sigmoid, which will put it between 0 and 1, and then that can be representative of our confidence that this is a real example. Okay. So there, looks like we've done everything, right? We've gone through conv 1, batch normalization 1, activate, conv 2, batch normalization 2, activate, reshape it so it's got the right number of dimensions for our fully connected layer input, then through the fully connected layer down to 1 dimension where we apply a sigmoid to put that in the range we want, and then we'll return our transformed x, right? And so this has gone from image to probability. Yes. Yeah, you could. I mean, you have to. Yeah, like you don't need the fully connected layer. For instance, you could just. Well, actually, I think you do need the fully connected layer unless you can somehow convolve down to a single unit, right? And then you could do it fully convolutionally. But yeah, the point is that you want to just convolve until you've got like a complex representation of the object where each feature has some meaningful representation, and then take a linear combination of them just as a simple operation to combine them in a learnable way into a single value. I think it's an easy way to do it. Okay. Any other questions at this point? Cool. All right. So yeah, we did that. We made the discriminator. Cool. Now we'll do the same thing for the generator, and so this is going to go so that one went from image to confidence. This one's going to go from latent vector to image. So we'll start off with a class, and we'll call it generator, which inherits as always from torch.nn.module. Okay, then we'll define the constructor for it. So how does that go? Take self, classic, call the parent constructor. And then what? Then we're going to define our layers. So this is going to go. What we're going to do is we're going to give this a some random noise, a latent vector, and that's it's just going to be a vector. So we're going to do some fully convolutional layers on that, and then we're going to change that into a tensor, and then we're going to up convolve that until it matches the same size as all of our images, which is 28 by 28 by 1. Okay, so we'll define firstly our first dense layer. So we'll say dense 1 is equal to torch.nn.linear. And that's going to go from the dimensionality of our latent vector, which I'm going to put as 128. And it's going to go to some intermediate value, so put 1024. Then we'll have another dense layer, torch.nn.linear again. 1024, actually the way I've done this before, sorry, is 256, 256 to 1024. Okay. And then we'll have another dense layer. Torch.nn.linear from 1024 to 128 by 7 by 7. Okay, and then given the specific convolutional layers I'm going to define now with their given kernel size, stride, and padding, this is going to be the shape which we need to perform each of them sequentially, such that it ends up as a 28 by 28 by 1 output for each example of the batch. Okay, cool. So dense layer's done, and then we'll have two up convolutional layers. So uconv 1 equal to torch.nn. This one we haven't seen before, so this is conv transpose 2D. Okay, and this takes in, similarly to convolution, the number of channels in, which in our case is 128, the number of channels out, which we'll say 64, the kernel size. The kernel size is equal to 4. And stride equals 2, and padding equals 1. And then we'll say self dot upconv 2 is equal to torch.nn.conv transpose 2D. From 64 channels to 1 channel with the same, 4 to 1. So yeah, 64 in channels, 1 output channel, 4x4 kernel, stride of 2, padding of 1. Okay, and then we'll also have some batch normalization layers. So self.pn1 is equal to torch.nn dot batch norm, and these are going to be on the output of our dense layers. So these are going to be 1D. So batch norm 1D. How many neurons are there in this output? 256. Okay. Self.batch norm 2 is equal to torch.nn.batch norm 2D. Sorry, 1D again. And in this case, 1024. Yeah.
Is there any reason why you settled on this kind of architecture?
Just so the dimensions work out. If I change one thing, I know I'll end up just like playing around with it to make it all fit together. Because it's like the convolutions change the activation map slightly, and then when you flatten the image, and if you change the image size, it's all gonna like mismatch slightly.
In terms of the sizes, but in terms of saying moving from you have 3 linear layers, it could have just gone.
Just because it seems to train this way, that's why as well. Yeah, just experimentation. But yeah, like feel free to definitely play around with it. Get hands on and see if you can break it, see if you can make it better. I don't know how good results we'll be able to get with this today, but at least you can see it does work somewhat. So self.bn3, and this is the output of our third convolutional layer. So we'll say torch.nn.batch norm 1D on 128 by 7 by 7. Okay. And then we'll also have a self.bn4, the last one we'll do, torch.nn.batch norm, and this is on our 2D convolutional outputs. So, well, at least we're doing the normalization over 2 dimensions, and that's going to take in 64. So if it's 2D, it takes in the number of channels which are in that activation map stack. Okay. Yeah, that's all the layers we want. Now we're going to do the forward function. So define forward. Then we'll go, yeah, we need self, and we'll take x, some input. Well, actually, you know what? This is z, okay? So we'll say z is equal to stuff again. Self dot activation function is equal to torch dot nn dot relu. Yeah, and we're also going to put sigmoid on the end of this one as well. Why? Because it's a grayscale image. So all of the pixel intensities can be represented as numbers between 0 and 1. So say self dot, again, sigmoid is equal to torch dot nn dot sigmoid. Okay. So our latent vector comes in, our random noise comes in, okay? And what we're trying to do is learn what each of those parameters represents in this space which we're making up, which we're going to transform into our realistic output. Okay. So, so the first thing we're going to do is pass that input through our first dense layer. So self dot dense 1 of z, and then we'll transform it with batch normalization for that layer, and then we will activate it. Self.activation function on z. Yeah, dense batch normalization activation function. Then we'll do the next dense layer. So self.dense2, self.dense2 on z. Same thing again. This is repetitive. Batch normalization 2. And then again, activate. Okay, cool. Done the first 2 layers. It's going to be deep. You know what? Let me just self first. Yeah, let's just do this. So we'll stack it all in one. So this is through the first layer, which has activated, batch normalized outputs of dense 1. And then we'll do the batch normalized self-dense 2. And then we'll activate that. Okay. Cool, so there's the first 2 kind of like compact layers, which consist of fully connected layers, batch normalization, activation function. And then we'll say, so for the third layer, what we got? We got another dense. Okay, cool. So self.af, self.batch normalization 3 on self.dense 3 of that z. Okay. And now we've done all the convolution. We've done all the fully connected layers. Now for the up convolution layer. So the output of that again activated, batch normalized, self.uconv1 on z. Okay. Everybody still with me? simple, repetitive, right? Cool. So we've gone through linear, up convolution. Now, on this last layer, we're not going to use that activation function. We're going to use the sigmoid. This is our output layer. And then that's just self.upconv2. Yeah, uconv2 on Z. Okay. And we'll return Z from that. Okay.
Is there a reason why you don't use batch normalization in the last convolution?
The batch normalization is just a stabilized training, but it just adds more parameters, hence makes the model slower and the memory constraints greater. So it seems to work somewhat with this, but it, you could add it, yeah. No. But yeah, like, I'm sure you guys are, like, you can see now, like, it's really flexible. You can add in whatever layers you want really easily, and then just play around with it. If you use variables for the dimensions as well, it makes it more modular. But yeah, I trust you all to be able to like mess around with this stuff now and create better architectures than I've done. So that's that class defined. I think that's good. And now is the What time is it? Okay. Yeah. All right. So here, right, what we're doing, we instantiate the discriminator. We instantiate the generator. Better form. Define the number of epochs. Define the learning rate, both for the discriminator and the generator. We're going to have two different optimizers, which is why we need to do that. And this is what I was just saying to someone about how easy it is to split the scope of the parameters which you want to optimize with PyTorch, because the optimizers just take in what parameters are they basically allowed to affect. So we're just passing the discriminator parameters to this optimizer. Going to use Adam as well. And then, yeah, get a discriminator optimizer and a generator optimizer, pass those respective learning rates in. Okay. Then just for visualization and plotting, we'll define an empty list of the discriminator costs, an empty list of the generator costs, turn on interactive mode, make a figure, then set up a subplot on that figure. So it's going to look like this, where it's got one axis on the left and one axis on the right. So this is in row. Yeah, the grid has one row, two columns, and this is the first one here. That's the loss axis. Set the label to batch, the X label. Set the Y label to cost. Set the X limit to there, because you can see when it trains, really the interesting stuff is down there. And then we'll make another image, an image plot to add. So we'll just add another subplot on the right hand side, which we're going to put the generated image. We've got interactive mode on, so we won't need to close this or finish with it, and it can keep updating. So we'll just show it, and then it's ready to go. All right. So there's our nice setup. All right, batch, cost, empty grid. Now we're going to define the training loop. And so, yeah, how does this look? So we'll define, as usual, a training function. We'll pass in nothing, actually, just leave it. Epochs. And then what we'll do is we'll say for what have I got up here? Dcosts, gcosts. Okay, cool. So we'll say for epoch in the range of epochs, go through all the batches. So for batch, index, batch, that batch actually consists of real underscore images, and I think the fashion mlist then comes with a class label of what type of garment it is as well, whether it's a shoe, bag, jacket, etc. And that's kind of like that's the Y in the output. So when we cycle through our training loader, what it returns us is image class label. In this case, we're just learning from the unsupervised data set of just the images. So we don't want this one. The standard thing to do in Python is give that an underscore as a variable name, because we're not going to do anything with it. So for the batch index and the batch in enumerate, so counting through the, did I call it train loader? Yeah, train loader. What are we going to do? We're going to train the discriminator, train the generator. Yeah, so enumerate just pairs us with a number, gives you the batch index with it, and we can use that for plotting and counting up. So now we're going to create the latent vector, the random noise. So we'll say z is equal to torch.randn, and we'll give that 128 dimensions. And yeah, batch size by 128, and this is going to go into our generator. And from those 128 random, normally distributed numbers, we'll try to come up with images, which at least will be better at improving the generator, the discriminator over time. Okay. Any questions right now? Yeah. Yes, 128 is the dimension of the vector. That's how many elements in the vector. Could be anything. The larger it is, the more things you'll be able to represent. So you have a larger latent space, and hence, like, I don't know, if you want to generate from it, each of them might mean something different which you care about. Yeah. Cool. Any other questions? All right. We've got that latent vector. Now we're going to generate some images from those. So we'll say generated images is equal to what we're going to pass through the generator, right? So we have this generator, G, and then we'll do G of Z. Okay? And then we'll do the the prediction of the generated images. So the generated images prediction is equal to, now it's going to go through the discriminator of generated images. Okay, and then we're going to have the real predictions as well. So we're generating some random images with the generator, get them, pass them through the discriminator, and then we'll get the discriminator's prediction on the real images, which came from this batch. Okay, so we'll say real prediction equals discriminator on the real images. Cool, right. And now we're going to define those loss functions which I showed earlier. So dcost is equal to negative torch dot sum, so sum over overall the output for the batches, torch dot log, so that log probability of the predictions of the real images, right? Real images, real predictions. So there, see, like I said, breaking down that loss function, that's what we need to write for that loss function there, for the discriminator. And then we can say gcost is equal to negative torch dot, again, sum over the batches. This one, we're going to do torch dot log, log on the generated image predictions. And I think I divided by batch size here in the notebook, just because it gives a better update step ratio. There are different things you can do, like you can one basic but early technique for stabilizing the training of GANs was to train the generator like for many more steps. So if, like, so here you just have like for 50 steps do the generator and then go and do one discriminator step. And so that can sort of balance out the training, because otherwise I think even what someone just said to me, the discriminator can get too powerful too quick and be able to adapt so fast that the generator can't keep up with trying to generate good images from that. Okay, cool. So we've got these loss functions here. No, sorry, I missed the second term on this one. So obviously the discriminator cost contributes on how well it's doing on the real examples, but also how well it's doing on the fake examples. So torch.sum, torch.log. The log probability of the discriminator predicting this is real, but actually it's the 1 minus that, isn't it? So it's this, but with 1 minus generated predictions. Okay. And then we'll say, what do I call it? Yeah, the discriminator optimizer, D underscore optimizer, optimizer dot 0 grad. So yeah, 0 the gradients, otherwise they accumulate over time. Then we'll do dcost dot backward. So how does the cost change with respect to the parameters, with respect to everything which contributed to it? Store those gradients with those tensors, and then deoptimizer dot step. Okay. Yep. Okay. Cool. And now we're going to do the same just for the generator. So goptimizer dot 0 the gradients again, and then gcost dot backward, and then we'll do goptimizer dot step. Okay, looks good, doesn't it? And then what we're going to do is we're going to visualize this example every so often. Yep.
Shouldn't you put it in torch.new-grad?
Sorry?
Shouldn't you put this step within the torch.new-grad?
You're right, actually. Yeah. I'm not going to do that though. I'm going to do what is it? This one, so dcost dot backward retain underscore graph equals true. So what that does is once you do backwards on a variable in the computational graph, it clears all of the gradients to free up memory, so things run faster and you've got more space to do stuff. This retain graph keeps all the gradients which are stuck in that graph. Otherwise, when we go to do this generator update, there'll be no gradient in there. Okay, thank you for that. Good point. Yes. The discriminator loss. Yeah. So what is that? So you're saying that because it's different to the slides, right? Because I think that was a maximization and this is a minimization. So it's just the negative of that. Yeah. I hope that's right anyway. Okay, cool. So, and then every so often, we're going to put in that generated image subplot a visualization of what we're generating. So we can get the numerical loss and also the visual loss. So we'll say if batch underscore index is equal to 10,000, then what we'll do is we will put the the generator in evaluation mode, and that is because batch normalization behaves differently between training and testing. So during training, batch normalization, what you're doing is you're normalizing each batch by the mean and the standard deviation of the activations in that forward pass. During during evaluation time, what you're doing with batch normalization is using a running total that you got during training, because you'll probably be dealing, you might just be doing inference on one image, which is an extreme example, which then won't have the same kind of distribution as you were looking at during training. So you use the running average of mean and standard deviation during train time for batch normalization. So we need to put it in evaluation mode. And then what we'll do is we'll get some random noise equal to, again, torch.randn 1 by 128, and then get a generated image. So here we just did 1 instead of batch size as we did earlier, because we just want to see one example. We don't want to have to do inference on however many examples we've got in our batch. So generated image is equal to G of our noise input, and then the generated image image dot generated image. That should be. Sorry to give confusing names, but this is the plot, and this is the actual tensor. So generated image dot imshow generated image dot detach. So detach it from the graph. Otherwise, it's got I think it's got gradients and stuff, and then PyTorch just says no. So detach numpy. Not numpy. What this is going to come out as is something of size, batch size by channels, by width, by height. And when we want to show it, we don't want the batch size. So what we're going to do, and that's only going to be 1 anyway in this case. So there is a function we've used called squeeze, which squeezes off all the extra unuseful dimensions. So if we have a 10 by 1 matrix, that'll squeeze it into a 10 vector. But in this case, we're just squeezing off the batch dimension. Generated image dot detach dot squeeze. Is that good? And then another thing, the color map that we want to use is equal to gray underscore R. Otherwise, it shows up in a nasty neon green color. All right. Once we've done that, we'll do G dot put it back in training mode. So switch batch norm again, and then what we'll do is, because we wrote our own loss functions in this case, different to what we have done in the past by using Torch's loss functions, and by default they average over the batch. So we'll just divide them by the batch size. So dcost divide equals by batch size, and then gcost divide equals by batch underscore size. Okay. And then we'll do a nice print of everything that's going on here. So what epoch are we on? What epoch are we at? That's epoch. What batch are we at? That's batch index. What is our current discriminator? Loss. Dcost.item. And then what's our current generator loss? So G loss g cost dot item. Okay, looks good. Now we want to plot them, so we'll add them to those lists we made earlier. So we made these lists: dcost, gcost, dcost dot append dcost dot item, and then gcost dot append gcost dot item. Cool, right, and then yep, and then we'll plot them. So loss axis, which we made, dot plot dcosts in let's say red, and then the loss axis plot gcosts in blue. All right. And then final thing, fig dot canvas dot draw, just to update our plots. All right, is it going to work? Is it going to work first time? Probably not. Train epochs, which we defined. Let's do it. Invalid syntax. Okay. Okay. Who knows what this error is? So expected a four-dimensional, had a four-dimensional weight for a two-dimensional input. What have I forgotten to do? It's here in G of Z. So we're trying to generate something. I think you got it. Exactly. Yeah, I've given it. I think I think that's error anyway. Yeah. So in the generator, yeah, we need to review this. So we come through our dense layers up to dense 3, and then we do z is equal to z dot view -1. So now we've told it to come out of there as 128 by 7 by 7, and I guess that is equal to 6,272, but it wants 128, so we just need to resize it. Yeah, so I don't care how many batches. I want 128 different channels, and I want 7 by 7, I think. See what's up now. And it takes 2, takes 1, but 2 are given. Torch end or sigmoid. Yeah, okay, cool. Well, this error. Come on, guys. Okay, this is a class, I think. So when you create this, it's callable, and then you can call it with X. But when you initialize it, it doesn't take X; it just takes self. So where have we done that? In forward self X indiscriminator. Really? Self-convoy. Did I write that? Where is that? Nah, I must have just not run the cell. I must move from last time. D underscore optimizer is not defined, but I know what that is. Alright, let's do this. Go. Okay, so what's happening? That's what's happening. So there's our generator coming down, and see the discriminator starts off really well. Just, you know, I can tell them easily apart because the generator's not doing anything. And now they're approaching. You should see an example at some point too. You know what? Actually, let's just. That went relatively smoothly. I thought debug would take a lot longer for that. Okay. Oh God, what's happening? Alright, there's something. See, now note how that would have been totally random noise as well to start. Oh, that's not looking good. Maybe it'll come back down. But it's already got an idea of some shape, maybe, right? Oh God, doesn't look like it's coming back down though. It's going right up. Okay, alright. Oh no, come on. Yes, that's it. Back on track. Let's go, yeah. Come on, bring it back. Nah, I don't know why that happened. The kernel died. Is that going to keep going though? Okay. That looks way less pretty than it did earlier when I run it. I'm not sure what's going on. I don't know why the images aren't updating either. Oh yeah, I do. Stupid. Here we go. Look, so there's a random start. Okay. Oh gosh. I set a limit on the y-axis as well, so I can't see how far it's gone back up. Come on. It's been no sign. That was an interesting start. Strange. So yeah, like that's a GAN working. I don't know how good it'll get, but so what that's doing, just to run over again what we've done today, we took some random noise, we gave it to a neural network, and we told that neural network to change it from a vector into a tensor, and then upsample it using those learnable up convolutions until it's the same size as an image that matches the same, with the same dimensionality as what's in our training set, and then take that image and pass it through the discriminator. And the discriminator is another neural network which is meant to take image to classification of whether that's real or not. And we're switching between passing the discriminator real images from our dataset or fake images from our generator over time, and then evaluating how good they're doing, how well is the discriminator correctly classifying real images as real and correctly classifying fake images as fake, and how well is the generator producing samples which fall the discriminator. And then as we pass those to a loss function, which do those two things, after we found the loss, we differentiate that with respect to all the weights in each of those two models for two different loss functions, and update them so that they should get better at doing those two different things. I don't know how good this is going to get. It's learned something. Not coming back down again. So we'll see what happens there. On another note, thank you for coming, basically. Thank you so much for all coming to the Academy of AI. I know some of you have been really dedicated to it and been here basically every week, if not a few. Right now, I'm going to send you a feedback form, and you're all going to fill it in for me. I know you are. And tell me, tell us what's been good, what's been bad. And then, okay, I'm going to do that now so we can all do it. What's the best way to do that? Just left this on the other page for you, shouldn't I? Okay, you're all on this. You're on this email. I'm just going to send you this. Cool, and then I'm also going to send you a link, which I'm going to tell you about in a sec. All right. Okay, so you'll get that email. And let me know if it doesn't come through. Okay, on another note, if you have any, if you want any help or assistance from me and a bunch of people who really love deep learning and want to help you guys to deploy what we've taught you here and help you learn more, then you should sign up for deep learning office hours. So every Sunday we'll do a half hour or 15-minute half hour video call with you, and just we can just brainstorm about ideas, we can discuss problems, we can debug, you can tell us feedback, whatever, any kind of thing, help with projects, advice, I've got this bug in my code, I've got this thing working but it won't train, can't get the loss low enough, then sign up to this. I should have sent out on the link as well, but basically help with problems if you want it and it's related to AI. So fill that out. Let's have a look how this is doing right now. Okay. It's looking a bit more something. Okay, we'll leave that to go for a bit. Yeah, so you all done the feedback, right? Everyone's done the feedback, please. Okay, should probably stop shouting this and that.